Sébastien, now I'm going to turn the presentation over to you. If you don't have any question,
no, that's all fine.
ask. By the way, you can share your presentation.
Yes, can you see my screen?
There's a polling question, right?
Exactly, so that's correct. So perhaps, Jaren, you can start the first polling question. So here the idea is to understand a bit better about our attendees. So if you can just select in which specific industry you are working in through the small form that will pop up now in your Teams window, then at least we will get a better idea of the type of audience that we have. So I see that results are coming in. That's very good. So I would say that mainly what I see, at least half of you are working in the automotive industry and 1/3 of you in the aerospace and defense. And yeah, a very small part, at least just one attendee is working in the software and internet industry and another one in the I&M industry for industrial automation and machining. But okay, half of the audience is automotive and the rest is basically aerospace and defense. Okay, so the first part of my presentation will be on battery management system. So here I think it will be especially interesting for the automotive industry people. And then the rest will be more about signal processing and code generation. So here I think signal processing applications can fit to all the different industries that we have seen there. Okay, very good. Okay, so as it has been mentioned before, so we will start with a case study of hybrid electric vehicle battery management system. So here the idea is really to focus on the battery itself and how to create a controller in order to handle the plant model of this battery. So that's what we are going to see right now. So that's the small agenda for this first session. In the first part, we will see how we can model our battery plant. Then we will see how we can indeed simulate it, test it, not only on the controller part, but also on the plant part. And then we will see how we can generate code out of it and deploy it onto an embedded system. So here I have a second question for you. So now it's for me to better understand your experience with the different tools that we have. So Jaren, if you can start the second polling question, that would be great. And here it's a multiple choice question. So you can just select indeed with which tool you have already worked, with which tool you are already familiar. So out of MATLAB, Simulink, Stateflow, Simscape, and code generation. Okay, so here again, I see that inputs are coming in. So yeah, so a lot of people know MATLAB and Simulink. I think almost all the attendees know MATLAB Simulink. A good set of people also know Stateflow, also code generation, and a bit of Simscape. So, but yeah, in general, so there are more than 30 people already knowing MATLAB and Simulink, and more than 15 people already knowing Stateflow and code generation. Okay, thank you very much. So that's very good. So at least I know that you already have some experience with our tools, and that will make things easier. Okay, so let's just define what will be our case study for this first session. So here you have a model of an hybrid vehicle. And you can see that you have the charger, for example, there, the battery component, then you have the electrical motor, the power electronics, and so on. And you can see that you can model such a system using our system engineering solution. So it's something I'm not going to talk about today, but just to make you aware that we have a system engineering solution for such complex system that is called System Composer. And you can see here in the lower right corner how it is. So indeed, it's a component and the pipes tool in order to model such a system. And here you can see that, for example, for a system like this hybrid vehicle, you will have, for example, the battery here, the DC-DC converter, the motor, and so on and so forth. And in our case, we will just focus on the battery for this one. So that's the battery pack that we have there. So this is how the battery pack looks like. So as you can see, we have several battery cells that are connected together. So what we will first do is that we will have a look at one single battery cell. We will create a model out of it, and then we will try to estimate the different parameters that are within such a model. And then once we have created the model of one single cell, we will replicate it for the number of cells that we need in our battery pack. So as you can see, for one single cell, so the current and the voltage are tightly coupled in such a system. And we have decided for this application to choose a specific current that will evolve over time as the input of the battery. And you can see that this current is indeed a negative pulse charge, okay, that will indeed drain energy out of the battery. So the goal is really to discharge the battery with such input current. And then, so the observed behavior of a battery voltage under a pulse input current is represented here below. And you can see that it is made of constant, instantaneous, here in red as well, and exponential changes in green in the battery voltage. So we want to reproduce this behavior in order to later achieve a digital twin of the battery package. So here we can see in blue the constant behavior of the voltage here and there, in red this instantaneous change, and then in green the exponential relaxation. So in our case, we have a lithium-ion battery that works following a chemical process. And here what we can do is that we can create an electrothermal analogy to this process that is called an equivalent circuit. And that's what you see, that's what you see here in the lower left corner. Basically, we can model the chemical process of a lithium-ion battery by having an internal voltage source, which is this EMF here, an output resistor, which is R0, and a pair of resistor and capacitor that is indeed our branch of our battery. And now we will go a bit more into details regarding these parameters. So this equivalent circuit is a way to model a battery cell. You could do other equivalence implementation if you want, using mechanical or something like this. But here in our case, we took the electrical domain in order to build this equivalent circuit. And the model contains few parameters, as you have seen. And these parameters can be tuned to reproduce the voltage change over time. And it can be observed that the output resistor R0 mimic the instantaneous response in the change of voltage. So that's the red part in our voltage signal. Then what we can see also is that the pair of resistor and capacitor R1, C1 allow to determine the exponential relaxation that you have there in green, in this part and in this part. And also that there is the input voltage source, EM, that allow to mimic the open circuit potential. So that's the constant voltage that we have. So indeed, the exponential curves that we see on the right-hand side are given by the sum of exponentials with different time constants. Depending on the level of accuracy required by the application, we may want to increase the number of RC parallel circuits. So here we only have one time constant that is given by the product of R1 with C1. And if you want to make it more accurate, to have a more accurate model, you can increase the number of parallel RC circuits, one after the other. You put them in series, and then you will have more time constants. So, but then in this way, you will have more parameters in the model that have to be tuned in order to replicate the battery response. So in our case, we will keep a simple example with only one time constant and these 4 parameters that we need to tune in order to mimic the real behavior of our battery. So now let me jump to MATLAB and Simulink. right here. And I will open the very first model, which is this one, this cell 1RC estimation. And this is how the model looks like. So I have seen that in the previous poll that some of you know Simscape, but not a lot. So here I will provide you some more information about Simscape because that's what we are using there. So first, you can see that on the left-hand side, we have some input signals that are coming from Simulink. And you can see that in Simulink, you always have an arrowhead that will indicate the direction of the signal. In Simscape, for search a physical signal, you don't have any arrow. It's because within the physical domain, which can be electrical, mechanical, fluid, thermal, or whatever, the energy flux can always flow in both directions. So that's why there is no arrowhead. As an example, if you take an electromechanical motor, so you can apply a voltage difference at the input of your motor, and then the rotor will turn. But what you can also do is that you can turn the rotor manually, and then this will produce a voltage difference at the input of the battery. So that's why we don't have a specific direction for such physical signals. It's because they can go in both directions. So here what we do is that we have an input current that is a reference current that we have measured onto a real battery. And then we provide this input current to our battery. So the only thing that we need to do is that we need to use our Simulink signal into a battery current ideal source. And then this one will convert the current into a physical signal. And then we will connect this to the battery. And after that, so when we will drain energy out of the battery, the voltage difference that you can see here, and that is measured by this voltage sensor, will be provided as the output estimated voltage. And then the goal for us is to compare that this estimated voltage is the same than the real voltage we have measured onto the battery when we did real measurement. And this is this one. That's the reference voltage. So we need to compare both of them. So now if I go inside the battery, so first you can see that this subsystem is a variant subsystem. I don't know if you're familiar to that, but you can see it on the lower left corner. There are two small squares, and this means that this subsystem can have multiple implementation of its algorithm, not only one, but it can have many. So here in my case, I will just go into the first one, which is the components representation. Okay. And now you can see our model that was shown in the slides before. So we have our voltage source internal. We have our pair of R and C components. We have the output resistor. And then what we need to do for our battery, we need to retrieve an information that is very important, which is the state of charge of the battery. And that's why here we have a sensor in order to measure the current. And then we can extract the current, convert it as a Simulink signal. And from there, we can integrate over this current over time and find out what is the current state of charge of the battery. So here, as we will drain energy out of the battery, what we do is that we set the maximal capacity of the battery to 100%. That's why here I have the value 1. That's the maximal energy the battery can have. And then every time we will remove current out of the battery, indeed we will integrate over this current that is removed. And that's why here we do the maximal value minus the current that is taken out of the battery. And we just need to normalize the current with a factor there, which is indeed the capacity of the battery. And within the units of the battery capacity, this one is indeed mentioned in hours. And here in my case, I need to integrate every second over the current. So that's why I just do the conversion by multiplying this factor with the value 3600 to convert it from hours to seconds. And now I will do indeed the Coulomb method in order to integrate and compute the current that is flowing through the battery. So now let's simulate this and let's have a look to the result that we will get. So here on the right-hand side, now you can see that we have the input current that is made of these negative pulses that will indeed take out energy from the battery. So that's exactly what we want. So we have 10 of these pulses. And here you can see at the bottom the state of charge of the battery. So at the beginning, the battery was full. And at the end, after we have taken out several times current from the battery, then the battery is empty at 0. So that's perfectly fine. But now, if we look at the estimated voltage that is in blue, and if we compare it with the measured voltage on the real battery, we can see that both of them do not match. We can see that there is only at one specific state of charge, which is the 7th one, that both signals, both voltage are indeed the same, but they are not the same for all the others. And that's because in our model that we have there, we have just defined one value for the capacitor, one value for the resistor, one value for the input voltage source, and also one value for the output resistor. And the values that we have defined match very well with the state of charge number 7. But the thing is, we would need to adapt the parameters values for all the other different state of charge that we have. And as you can see with this model that we have created, this is not possible because we can only have one scalar value for each parameter, and then we cannot have a set of vector values for each of these components. And in order to do that, so that's something we can do with a specific component from the Simscape electrical library. And this is what is in my other variant. So let me select another variant, which in this case, it's the second one. And here you can see it's written lookup table. So my second implementation of the algorithm will use this subsystem this time, and it uses this Simscape electrical component, which is indeed a lookup table. And here, that's exactly what we want, because the advantage of the lookup table is that we will be able to define vector parameters. And here, perhaps, before going too quick in this direction, let me just come back to the presentation and show you how this works. So indeed, the lookup table for a lithium battery model, in this case, what we will do is that we have this table that shows the open circuit voltage, which is this EM value, versus the state of charge here in the first line, and also versus the temperature. So up to now, we have only modeled the electrical behavior of the system, and we did not take into account the temperature, but the temperature is very important as well. So here, with this lookup table component, we can take into account the effect of the temperature as well. And then what we will do is that we will have to do a parameter estimation of the values that our components should have in all these different state of charge cases and all these different temperatures that we can have. And with this approach, it can give an excellent flexibility for the model to match the real data, provided that the tables have enough breakpoints. So here you can see that we have 11 different values for the state of charge that are going from 0 to 1. And we have discretized them just by splitting them by 0, 1. You can be even more accurate if you add some internal state of charge, like you split it every 0.05, for example, value. But here in our case, we are accurate enough if we split it only by a factor of 0.1 between each values. And yeah, here the advantage is that we will have the thermal behavior that will be represented as well. That will indeed take into account the losses that you have within the resistors of the battery, and also the battery electrolytes that have some thermic behavior. Okay, so now the goal for us will be to estimate those parameters correctly based on the different state of charge that we have in our model. So for that, we have created our lookup table model with these 4 parameters. And now we give as input our negative current to the system. And then we will measure the outputs. That's what we have already done before, but only for one single state of charge. Now we will do it for all the state of charge. And then we will compare both output voltage the one that was measured onto the real hardware and the one that we got out of our model. And then we will have a look at the error between the two. And if the error is still too big, we will iterate again and try to modify the values so that we can converge to the ideal parameters. Sorry, someone is on mute. Can you please mute your mic? And then, indeed, once the difference is not accurate enough, we can always look back, tune the parameters, and then once everything is fine, we can save the computed parameters. So here, indeed, there are two ways in order to get out of this loop. Is either the accuracy is good enough, and then we can leave, or you have done a given amount of iteration, like for example 10, and after 10 iterations, you say, okay, that will be enough for my model. I can live with the values that have been computed. And that's what I'm going to show you right now. So here I did a video because it takes a bit of time to do this parameter estimation. In my case, on my computer that has 8 physical cores, it took 6 minutes to do it. So here I've done a short video to make it faster. And I have also taken advantage of my indeed computer that has 8 physical cores with the parallel computing toolbox. So let's just have a look at this video. So here we just run the simulation once, and you can see that we are in the same status than with the simple model I showed you before. And but now if we look at the values, so we have 11 values for the capacitor, 11 values for the input voltage, and you can see that all these values are exactly the same. So that's why it matches only for one state of charge. And now what we will do is that we will open this parameter estimation app, select the parameters you would like to tune, and then for each of these parameters, you can define also the minimum and maximum values that you can have. Because, for example, for a resistor, it does not make any sense to have a negative resistor. So you can set the minimum value to 0. And then once we have done that, we can prepare the app for the estimation, and we can take advantage of the parallel computing capabilities. If you have a multi-core desktop, you can do it. So here, I just need to select to use the parallel pool, click on OK, run the estimation. So you see it was pretty straightforward. And now what it will do is that MATLAB will create a parallel pool of workers that will take advantage of my 8 cores on my machine. And then once it is ready, I can quickly check in MATLAB that the cores have been activated. So you see, if I go to MATLAB, you can see that the workers have been initialized. And in the lower left corner, you will see that now 8 workers are working. So now it has started with the evaluation of the parameters. It has done the first round, the initial round with the initial values that I provided. And you can already see that after a first iteration, now the measured signal of the output voltage is indeed the simulated signal of the output voltage is the same than the measured signal. And now we can fine tune the parameter iterations after iteration. And here what I will do is that after 6 iterations, I will stop this process because as you can see, the accuracy that is provided by the pulse data column in our small app in the lower left corner is decreasing. So that means that the error is decreasing. And in our case, once we reach a given value, which is about 0.0018, if I remember correctly, then the accuracy is good enough and we can stop the process. So now you will see at the end of this message here that the process has been stopped after 6 iterations, which is good enough for us. Then once this is done, we can save the new parameters that have been computed. So I will save them as a math file to my battery folder location. And once this is done, I can indeed update the model to use this new set of parameters. And to do that, I just need to access to the callback of my model from the model properties. And in the callback, this is where I load the math file. So here you see, I'm just changing to use the ideal set of params, which are the ones that I have computed right now. And then I can close the model, reopen it, run the simulation. And this time you will see that now the parameters are exactly correct. and that now the output estimated voltage is the same than the output measured voltage. And now we can have a look to the parameters, and you will see that this time the 11 values that we had for the capacitor, for the resistors, and so on, have been updated, and now we have different values for each different state of charge. And that's what we wanted to do. So now we have a very good model of our lookup table for the battery. And also one thing I can quickly show you, if I go back, let me just close the Simulink model. I will just show you something that is very interesting. If I create, for example, a new Simulink model, I go there, and then I go to the Simscape library. So you see, you can access the library from there, and you can go in Simscape. And then in Simscape, you have all the different physical domains. And if you go to electrical sources, then you have this battery component that I showed you before, the table base, the lookup table. If I bring it here, and then I go inside the parameters, you can see that on top, you have click to select. And if you click there, there is one thing that is really, really cool, I would say, is that you can already have predefined values. So for the capacity of the battery, the nominal value, and so on and so forth, the time constant, and so you have already predefined values that are there based on the vendor that you would use for your battery. So for example, if you would like to use a battery from Panasonic, now you can see the different types of the batteries that you have, and you can select the one you want. And once you have selected it, then it will automatically apply all these parameters, and you don't have to do what I have shown you before. Okay, the process of doing the measurement onto the real hardware, then do the parameter estimation and so on. You already have pre-populated vendors that are there for the different type of batteries that you may want to use. And but this is only available with Simscape Electrical. And if this is something you need to do, I would really recommend you to do that. And this is not only available for batteries, but for example, for electrical motors, if you go to the electromechanical library, you also have the same kind of interface that will allow you to select the vendor of your motor, for example, Maxon, and then it will have also the set of parameters that can be directly uploaded. So this way you save time not having to tune the parameters or not having to enter the parameters from a data sheet. And I think that's something really cool I wanted to show you. Okay. So now let me go back to the presentation. So we had a look at one battery cell, how we can model it and so on. Now the goal is to create a battery pack. So we just need to replicate our different, our battery cell as it is shown there. And now perhaps I will go to Simulink and open another model, which is indeed the battery system. And here, so we will have the battery pack, as we have seen before, the pre-charge circuit and the charger and load. So that's my full system with the plant and with the ECU. So if I go inside the plant, now we can see that we have directly there. So the charger load, the pre-charger circuit, and indeed the battery pack. You can see the physical connection between these components. It's like before. And by the way, that's something I did not mention, but the blue means something. So there is a color coding for physical signals. If it is blue, that means it is an electrical signal. If it is orange, that means it's a thermal signal. If it is brown, that means it is a mechanical signal, and so on and so forth. So these colors mean something at the end. And yes, so now if I look, for example, at the pre-charger circuit, so here you can see that there are 6 different switching devices that we need to control to avoid undesired spikes between the battery, the charger, and load. So our BMS algorithm, our BMS logic will have to handle these switching devices so that we don't have any issue in the plant system. And then if I go back and I get a look at the battery pack, so here you can see that there is also a variant subsystem for this one. And then we have indeed 2 algorithms that are available. So it just needs a bit of time to open. That's why it's a bit, I think it's because I'm sharing the screen. Yeah, it takes a bit of time. So here we have indeed 16 battery pack modules, or just one. Yeah, so here we will keep one. So one, that means that we have created a model of one battery cell, and then we will replicate it 6 times, because before we have seen the 6 switches. So here, if I go in the subsystem that is on the left-hand side, we can see that we have the 6 batteries. So here, you see, we are retrieving our model of one battery. And in blue, as I mentioned, that's the electrical domain. But you also have now in orange the thermal domain that is modeled. So now I am also taking into account the thermal behavior of my battery. And you can see that we have 6 batteries. So at the end, more or less, the default voltage of one battery is around 4 volts. So if we have 6 batteries together, at the end, we will have 24 volts output, more or less. Okay. And then if I go one level back, there is also in the middle the cell monitoring unit. And this one is also made of switching devices, as you can see here, that can be managed by our control logic to balance the state of charge of the different cells. Because as you can imagine, not every cell will indeed decrease or increase the capacity at the same time. So here, this will indeed balance the state of charge of each cell separately. Okay, so that's for the planned part. So now if I go back to the presentation, now we will have to have a look at the battery management system, so our controller. And so if I go back to the Simulink model and I enter inside the ECU. So if I double click on it, you can see that this is again a variant subsystem, and it has 2 options: to use or not the AutoSAR software architecture. So here we do support AutoSAR Classic and also to some extent AutoSAR Adaptive. And so as you are working in the automotive industry, I mean, at least half of you are aware about AutoSAR, that this is a hardware abstraction layer that allows you to create your algorithm, your application at the algorithmic level, and then to share it. And you don't have to take care about what type of hardware peripherals are used by your ECU. It will automatically work. So here we do have support for that as well. But that's just informative. Here I will not take into account the AutoSAR architecture. I will just go in the normal BMS ECU that does not have any hardware abstraction layer. And here we have 2 implementations of it, either in Simulink directly, that's what we are going to have a look at, or in System Composer for system engineering. But I mean, that's not the most important. Let's go in the Simulink architecture. And here, as you can see, we have 4 different components that are in charge of several tasks. So at the bottom, there is the balancing logic to manage the state of charge of the cells. Just above it, there is indeed the state of charge estimation model to estimate the state of charge of our cells. And then on top, there is the main control logic component that is made of a state machine. And perhaps if I just go in the SOC estimation 1, just for your information. So here, in order to estimate the state of charge of the battery, there are many techniques in order to do that. The one I showed you before with the Coulomb method is also the one that you can retrieve there. So you will just integrate over time, okay? But then there are other models that can be done using Kalman filter, using also neural network approach, and so on and so forth. And this is just an example of what can be done, but there are many different techniques in order to do it. And now if we look at the state machine, which is the most important part there. So this is how the state machine looks like. So this one is done in state flow. So I have seen in the poll before that some of you know state flow already. And here what we have is that we have a state machine with 4 different main states that run in parallel. So let me quickly explain you the goal of these different states. So we have the main state machine state, this one, that indeed handle the way the battery is used. So first, there is the standby, which is the initial state, and then it's either charging for the battery that will be able to increase its voltage capacity. And then we have driving that will indeed take energy out of the battery. So these are the modes that we have there. And then we have some other main states that are, for example, fault monitorings in order to handle any misbehavior of the plant. Let's imagine that now there is one battery cell that has an issue, then this will be handled by that. And then you have the two states here at the bottom that are there to handle the different switches that we have seen before in our plant model of the system. So here we will definitely handle them separately for each cells. So that's what we have here with this battery management system. And now let me go back to the presentation. Let's see what I will show you first. So this, we have discussed it. Yes, so then I can perhaps quickly generate code. I think that's something of interest. So let me go to the apps, open the embedded coder. Yeah, this one. Okay, let me open the embedded coder. Okay, so now I have opened the model as a separated model because I don't know if you paid attention to that, but these are reference models. So when there is a reference model within your system, that means it's a completely separated Simulink model. So that's why I have opened this subsystem as another Simulink file. And then from there, I can indeed generate code. Okay, so let's generate code. I cannot build the code and deploy it onto the hardware because I don't have the hardware with me. So that's why I'm just showing to you code generation. And then I prepare the video on which I will do the deployment onto the real hardware. So now we are generating the code out of our state machine. And now this is one feature that is very interesting as well, is that you can see that once the code is generated, it will be displayed side by side with your model. And that's very interesting for bidirectional traceability between the model and the code. If I go inside my state machine, and now I would like to see where is the code of this specific state, I can click on it, and then it will bring me to the corresponding code directly. And as you can see, as we have a state machine there, when it generates code, so you could expect with a state machine to have switch case statement, if, else, and so on and so forth. And that's definitely what you can see there. So the code is easily readable. You can select what you want. It will highlight you where it is in the code. And for example, if I want to see, let's see, where is this? Sorry, where is this transition? Up, I can click on it, and now it highlights the transition, which is this one. And that is very convenient so that you can navigate back and forth between the model and the code. So for code review, for peer reviews, and so on, that is really useful. So I just wanted to show you that, this capability of generating the code and navigate between two worlds. And then regarding code generation optimization, I will go much more into details in this part in my second talk, which will be about ECG processing. Here I will go much more into details regarding code generation. So let me go back to the presentation. So now, once we have done the model of our system, of the plant part and the controller part, we would like to simulate this model. That is very important. So up to now, we just simulated our single cell, but let's simulate the entire model. So the first simulation mode is the normal mode of simulation that indeed has the Simulink model with the solver directly on top of MATLAB, and everything is running in one process. As you have seen, the system that I showed you before is quite complex. We have a lot of things. If I run it in the normal mode of simulation, it will take quite some time. So to make it faster, we have two other modes of simulation that are the accelerator mode that will do just-in-time compilation. So it will not only interpret the code, but it will already generate some code, but it will still keep everything together. With the rapid accelerator mode, the advantage is that what you can do is that it will compile the whole model and creates a rapid accelerator standalone executable. And this executable resides outside of MATLAB and Simulink and uses the external mode in order to communicate with MATLAB and Simulink. And also in my second talk, I will show you how external mode works directly onto the hardware. So at the end, the rapid accelerator mode creates a rapid accelerator standalone executable from the model, and it includes the software and model method, but as I mentioned, it resides outside of MATLAB and Simulink. So at the end, you will have two processes. So here, this will take also advantage of your hardware architecture. So if you have at least two processors onto your computer, both processes will be able to run onto the different cores. And this will speed up the simulation as well. And that's what I did here. So let me go back there to the stop level model. I had another model that was open. I will just close it. Yeah, this one I don't need anymore. So now what I can do is that here I have already created a test bench, or what we call the test harness, that is linked to my system. Okay. And this is how this test harness looks like. So test harnesses are available with Simulink Test. I don't know if you know this toolbox, but this is what is used for verification and validation mainly. And here for my test bench, I can provide several types of inputs. So here I have the signal builder block, which is an old way of creating inputs for a test bench. Now there is the more up-to-date version that is using the signal editor block. You have also the test sequence block that allow you to define a temporal time sequence and so on and so forth. And but here, yeah, we can use the signal builder. So you can see this is our input stimuli. So we just go from the balancing to the charging state. And at the end, we remain in the charging state. That's what it does. And then we provide this to our battery management controller, and then we measure the outputs. So let's just run this simulation. So you see, I am running it in rapid accelerator mode. You will see that for each reference model that were inside this battery management system, it will indeed generate the code separately for each of them. So you see, first it is taken the balancing logic, then the curve power limit calculation, and so on and so forth. So it will do that for all the different reference models. And that is something that is useful because with reference models, you can do incremental building. That's what we are doing right now. And you can take advantage of the cores of your machine. And also it does what we call incremental loading. That means when you open a model, it will not load the reference subsystems. It will only load them when you double click on the reference models, which is also saving some time. Okay, so now you see it has generated the code and now it is running in rapid accelerator mode. So we can see here the percentage of the simulation that is increasing. And I think I will have to hurry up because if you want to have at least 10 minutes for the questions. So I still have 3 minutes. So in the meantime, while it is finishing to simulate, so you see it takes a bit of time. Even this is the rapid accelerator mode, it takes a bit of time. So let's, in the meantime, go there and talk about software in the loop and processor in the loop verification techniques. So with software in the loop, what we will do is that we generate code out of the controller and still run it onto the desktop computer. And everything is controlled from within Simulink. With processor in the loop mode, we will generate the code for the target, deploy it onto the target, set up indeed a communication channel between the two. And this is a non-real-time simulation technique because when we set up this communication gateway, we check that all bits and bytes are indeed transmitted and received, so exchanged correctly between the hardware and Simulink. But at least you can run your full controller algorithm onto the real hardware, which is quite interesting. And this I will also show you more into detail in the next session. But in the meantime, now the simulation in our test bench is done, and we can click on the data inspector to have a look at the signals. And here you see, if I go, for example, so our input is called state request. That's our input, so I can select it. And now you can see what we had in this signal builder block. So from balancing to charging, balancing to charging, that's the only thing we do. And then I can have a look at the output signals that we have there. So for example, if I go to where is it already? Sorry, to the plant here, I can have a look to the pack voltage and the pack current. And now I can make this bigger, zoom on it. Okay, and here what you can see is that the pack voltage in blue. So you remember I told that we had 6 cells and one cell had an output voltage of 4 volts more or less. So you can see that we are around 24 volts, which is correct. And then when the battery is fully charged, indeed, we have this value here. So you see with the cursor, you can see the value. So we have 25 volts when the battery is fully charged. And you see that when it is fully charged and we are not taking out currents, so the current at the output is equal to 0. So now at this state, the battery is fully charged. But in the meantime, you could see that between the transition from balancing to charging and so on and so forth, so the current and the voltage has indeed changed. Okay, so I think that was what I wanted to show you. And now there is another polling question. So perhaps, Jaren, you can start it. So here the question is more about how do you test your algorithm? So are you already using, indeed, for example, MATLAB unit testing in order to do it? Or you are already using Simulink test, as I showed you? Or you do already software in the loop, processor in the loop, hardware in the loop, all these in the loop verification techniques. So let's see. So I see that inputs are coming in. So yeah, it's quite spread around the different techniques. So I can see that what you do a lot is model in the loop, but also hardware in the loop. So these are the two top. And then right after this comes software in the loop. Also MATLAB and Simulink testing. FPGA in the loop is not done. So that means that you are not doing HDL code generation. So this could have been something I could talk about, but as you don't do it, it does not make sense. So that's good. Co-simulation, only one person is doing co-simulation. Okay, but basically you are doing hardware in the loop, software in the loop, and model in the loop. So I will show you processor in the loop today with the external mode, and I think that could be interesting for you. Thank you for the poll. And yes, here that's just the deployment of this model onto the real hardware. So I have created a video. So let's go with the video. So here I am programming an NXP board, and that's why you have this small configuration block there for the NXP hardware. But here you see that's our test harness. And now, indeed, I can use the seal pill manager in order to deploy the code in pill mode onto the NXP hardware. And what it does in this case is that it will do a baseline run in simulation mode, so in model in the loop. Then it deploys the code onto the target. It does the run in processor in the loop. And then once you have done both of them, you can open the result and compare the model in the loop run with the processor in the loop run and see if they are both correct. And here you see that the results are all green for all of them. So that means that the results that we get between the code that has been deployed onto the hardware and the code that run in the model itself are exactly the same. And this kind of testing mechanism, you can automate them by connecting them to Jenkins, for example, for a CI/CD integration. And then in this case, all of this testing process will be automated. And only when results are different, you can set up the system so that it will send you an email in case there is results that are not correct. And I mean, that's good for continuous integration, continuous delivery workflow, if you can do these kind of things. And yeah, I think I'm done with this first presentation. So here, this is just a recap of what we have seen. We have seen physical modeling with Simscape. We have seen how to do parameter estimation and also how to implement the software part and to generate code out of it. And that's it. So now I will open the field for questions. So feel free to ask your question. We have, I would say we have 10 minutes for questions. And I don't know if there are questions in the chat, by the way. No, it seems there are not. So feel free to ask your question. Can you still hear me, by the way?
Yes, Sébastien, we can
Okay.
hear you. As far as I see, there is no question for this part.
So that was crystal clear for everyone. Okay.
Yes.
So okay, so then if there are no specific question, I think I will go on with the second part. And at the end, we will still have time for questions. So you can come back to the first part if in the meantime you got questions. Sorry. Okay, so let's move on with this. Good. So the second part will be more about, as I mentioned, signal processing and much more code generation. So here the application is about an electrocardiogram application. So the goal is to extract the electrocardiogram signals from a patient, and then out of this to compute the heart rate of the patient. So the first thing we will do is that we will model and simulate the full signal processing chain that we need for that. And then we will go to the automatic code generation part and integration with the real hardware. In my case, the hardware I'm going to use is an STM32 board with an ARM processor on it, an ARM Cortex processor. Okay, so let's have a look at the application itself. So here on the left-hand side, you can see the patient, and then we will connect sensors to the patient, one at the right arm, one at the left arm, and one at the ankle of the left leg. So we need to create a triangle around the heart in order to extract the electrical biosignal. And you can also create this triangle directly around the heart. You don't need to go that far away also. And then once we have acquired the data, we will bring them inside a data acquisition board, which is this red extension board that you can see there. And this one is connected to the STM Nucleo board below via the standard Arduino connectors. And here, what I have decided to use this board because it has an hardware abstraction layer that is called Mbed. I don't know if you have already heard about Mbed, but that is an initiative from ARM in order to create an open source hardware abstraction layer for the ARM processors that are Mbed enabled. So the goal is that once you have created your algorithm, your application, if you are using Mbed drivers in order to communicate with the peripherals that are onto the hardware, like an ADC, like an LED, or these kind of things, then you can retake your algorithm and deploy it onto whatever target that is Mbed enabled. And the goal is that there will be more than 150 different boards that will be supported with this kind of things. And at MathWorks, we have created a package in order to support that. And we are adding more and more boards time after time using this Mbed hardware abstraction layer. But that's why I've decided to use this board. And then once we have done our signal processing chain within the board, we will output the results. So here the results will be sent out via Ethernet using TCP/IP, UDP, and also a ThinkSpeak communication channel. So we can send it onto a local intranet network, but also onto the internet to the cloud. that was the goal of this. And here you can see the results. So the thing is, in blue, you can see the electrocardiogram signal, the row 1, and the goal is to indeed filter such a signal so that we just have the high frequency peaks that are there. And then for each high frequency peak, we detect them and we measure the time difference between each consecutive peaks. And then we do the mean value over 30 seconds, for example, and this will give us the heart rate in beats per minute at the end. So this is the idea of the application. And here, so I have modeled the signal processing chain. So you can see that the first part is about data acquisition. And then the second part is about the pre-processing stage. So here, for example, we will apply a pre-emphasis filter in order to increase the importance of low frequencies within the signal, because the frequencies of interest are mainly between 0 and 100 Hertz. And the most interesting ones are between 10 and 40 Hertz. So here we have this pre-emphasis filter that will increase the amplitude of frequencies that are between 0 and 40 Hertz. Then we will convert them from the analog domain to the digital domain. And here we have a bandpass filter that will take only frequencies between 10 Hertz and 100 Hertz. And after this, we will rectify all the pulses that we have so that we have no values between below 0, sorry. And then we will take the signal and pass it through a low pass filter in order to extract only the envelope of the signal. And once this is done, we will have to detect the peaks by doing the extraction of all peaks that are in the signal. And then out of all the peaks that we detect, we need to extract only the global maxima peaks. So that means only the ones that were linked to our high frequency component, not the other one. So here we put a threshold to define what are the peaks we need to select and the one we reject. And once this is done, we can compute the statistics of the signal and extract the values that we need, like, for example, the mean value of the beats per minute, the error on it, so the standard deviation, and so on and so forth. And then we can display the results. So that's what we are going to do right now. And here, what has been done is that the model-based design approach has been followed. So the idea is that first we start with the requirements. So here I did not gather in a formal way the requirements. I mean, in this case, that was not the most important. Basically, the requirements is to extract the beats per minute out of the ECG signal, and that's it. And then what has been done is that in the design phase, so we have created the processing algorithm following the model-based design approach. And I have also created a library of components, a library of IPs for reuse. So I will show you that after. And you can already see that we have two different implementations, one for the embed hardware abstraction layer and one for the STM32 low-level hardware layer, which is indeed directly connecting to the STM32 peripherals, bare metal, I would say. And here with embed, we have this added layer software in order to abstract the hardware from the application. And then in the integration phase, what we do here is that we have the drivers that are connecting to hardware peripheral via either this embed hardware abstraction layer or the STM32 low-level implementation. And here we will generate C code to program an ARM Cortex processor. And once this is done, we will go to the integration phase. And all along these phases, you have also the verification and validation phase. And here the goal is to be able to check that the model is already working correctly in model in the loop simulation mode, and that then the code that has been generated and integrated onto the hardware is working the same way by doing processor in the loop verification, for example. And that's what I'm going to show you after. So this is our first simulation model. So I can already explain it to you here on the slide. I think the quality is good enough. So you can see that on the left-hand side, we have the input signal that is there. So here what I did to simplify my testing that I did when I developed the model is that I recorded some ECG signals in a math file, and then I played them in Simulink. That was easier instead of always having the sensors connected to me. So here I'm just loading the 10 signals I have selected, and then here I can decide which one of the 10 signals I would like to use for my simulation. And then, sorry, the signal is flowing in there. And here you can see that there is the pre-emphasis filter, so which is our analog filter in order to increase the low frequencies amplitude. And then we have the conversion from the analog to the digital world. And here we have the bandpass filter, the rectifier, the low pass filter. Then we extract the peaks, the BPM final value, the difference between, the peaks time, the difference between two consecutive peaks, and then we compute the BPM final value. So you see that the signal processing chain we have defined before can be easily modeled in Simulink the same way. So we can easily understand what's going on there. And then we just display the results. So now let me go to this demo. So I will first close the remains of the previous one. Quite some windows that were opened. Okay, so now I will close this project and open the project for the electrocardiogram. This one, I will just clean the workspace. Okay, so now I have another project that I open, and this is this simulation model there. So here I also did something more. So perhaps I can show you with my camera. Let me just bring back the Teams view, and then I will show you with my camera. Perhaps you will be able to see it. So here I have the hardware. Yes, now you can see the hardware in the camera. So it's exactly the board I have shown you before. Plus, on top of it, I have added a 7-segment display module here that you can see at the tip of my finger. And this is exactly the one I have implemented there for simulation. So you see, if we go back to the model, I have created here my custom 7-segment display component using the MATLAB App Designer. So I don't know if you are familiar with the App Designer, but that is indeed a way in order to create graphical user interfaces. And here what I did is that I have created my custom 7-segment display component so that I can already simulate the behavior of what will be output to the 7-segment display component. And you can see this is done here by these 3 blocks. So if I have, for example, the value 123, so I first need to split the digit. So to make what you can see here, the hundreds digit, the tens digit, and the units digit. And then once this is done, I need to encode my digit because, for example, if I want to display here the value 1, I will have to enable this segment and this segment, but not the others. So that's what I do here, digit encoding. And then I am communicating through this system object. That's indeed a system object that is directly stored in the base workspace of MATLAB. And then here I will write to the system object using methods that are there in order to update the values of the segments. And if now I run the simulation, so you will see how it looks like. So I will simulate it for the signal number 6. And then you can see here the values that are evolving. And yes, sorry, it took a bit of time to update the 7-segment display. I think it's because I'm sharing my screen. This adds some delay. Perhaps if I rerun it, it will be a bit smoother. Normally, you should see the value changing on the fly. Yeah, you see 55, 56. So we could see it changing. So that's good. And now we have here all the different signals that we have measured at different steps, okay, of the signal processing chain. And if we look perhaps a bit more into details, so if we look at the bandpass, so here we have a bandpass component from the DSP system toolbox. And there you can easily define your own filter. So you see, you just need to specify what type of filter it is. In my case, it is an infinite impulse response filter of this order. And then as it is a bandpass filter, you can just define the first cutoff frequency, the second one, the sampling frequency, and the type of filter you would like to have, Butterworth, Chebyshev, or whatever. And then that's it, basically. You can easily model your filter like that. Click on View Filter Response in order to see if the frequency response is exactly what you think. So here you see we have the magnitude response, and that's fine. I wanted to indeed only keep the frequencies between 10 Hertz and 100 Hertz, and that's exactly what we have there. So that's fine. And for the other filters, it's the same for the low pass filter as well. It's the same. And then I will not go into the details, but for the others subsystems here, the algorithms are a bit more complicated, but that's fine. And I have created an IP library for all these 5 blocks because I will reuse them after this. So here I'm using them for the simulation, but then I will use them for the processor in the loop external mode implementation and also for the standalone implementation. Okay, I think that was clear. Then there is also the data inspector in order to see the signals. So perhaps I will remove the former signals. We don't need them anymore. And here, so if I go there, for example, have a look at the BPN mean, we can see how it goes. So, and we can see that at the end for this specific measurement, I had a beats per minute of 56, which is fine. Okay, so that was for the simulation. Now, if I go back to the presentation, which is there. Okay, so that's the IP library that I told you that I have created out of these blocks that I am reusing for the different implementation. And then here, we also have the variants that will be used as soon as we are accessing to the hardware peripheral. So here, you could see that I did not access any hardware peripheral for the simulation. I just run it locally on my computer without accessing any external peripherals. But for the peripherals, so you can see that I need to access to an ADC, to LEDs, also to some buttons. So you see here the reset button, and also to the network, UDP, TCP, IoT, and so on and so forth. And for all these variants, so in the very first session, I showed you how you can select variants by right-clicking on it and then selecting the right algorithm you would like to use. All this can be automated by using variant control and variant conditions. So for example, I can define a condition that is called embed. And based on the value of embed, if embed is equal to 1, for example, I will use the embed implementation. Otherwise, I will use the STM32 implementation. So this is how we can automate this. Then, in order to communicate with the peripherals, there are several things in order to do that. And especially when it comes to bring C code in the model, because here that's what we need to do now. We need to bring C code from the peripherals directly in the model. So you see there are 5 different ways in order to do that. The first one on the left-hand side, which is called the C color block. This one is just there to bring a basic C function in your Simulink model. For example, a C function that has some inputs and that will provide an output based on a mathematical operation. And that's it. That's the only thing it will do. Okay. Then there is the C function block that allows you to handle states as well. Let's imagine now in your mathematical operation, you would like to integrate or to compute the derivative. Then in this case, you will have to handle the internal states. And this can be done with the C function block. Then there is the MATLAB system object. And this is the technique I have decided to use in this project in order to communicate with the hardware peripherals. So here, the MATLAB system object is indeed a mix of MATLAB code and C code. So you will create a class, like a standard MATLAB class. And then in your class, you will define methods, you will define attributes, and so on and so forth. And you will also call C code inside C code that belongs to the libraries of the vendor that you are using. And this is what I'm going to show you after. And then you have two other methods, the S-function builder and the S-function itself. And both are the same. It's just that the S-function builder will help you to create indeed the wrapper in order to bring the C code in Simulink and so on and so forth. And the S function, you have to do everything on your own. So you have to bring the C code to do the wrapper on your own and so on and so forth. So this is for the advanced C programmers, I would say. But with these two techniques, you can also do everything in C, handling states, handling multi-rates, and so on. Good. So here, I will show you, I will open after that the ADC subsystem and show you the implementation. So you can see that in the case of the embed implementation for the ADC, you only have two parameters. You just have to select the pin on the board following this Arduino standard between A0 and A5, and you need to provide the sampling time. With the STM32 implementation, you have much more parameters, and that's what I'm going to show you now. So I will close the simulation model and go back to Simulink. And now I will open the external mode model for the processor in the loop simulation. And now you see that the model is more or less the same than the one before. We always have our bandpass, rectifier, low pass, extract peaks, and so on. But now we have the ADC input. And here, so you see that the analog signal is coming either from the embed hardware abstraction layer or the STM32 implementation. And if I open this embed hardware abstraction layer, so that's my system object. And by the way, this is part of the hardware support package that provides you all the drivers for the search peripherals. Okay, so if I go inside the library and I search for the STM32 hardware support package, so my board is the STM32F7. So you can see here already some blocks that we have for TCP, CAN communication, and so on. But if you go in the command blocks, you see all the ones that are using this embed hardware abstraction layer. And here you can retrieve this analog input to read data from the ADC. Okay, so all this is available in our hardware support packages. And now if I double click on this one, so you can see that the interface is very simple, just the pin and just the sampling time. Now, if I go in the STM32 implementation, now the mask is much more complicated because here indeed, I am connecting to the source code of the subroutines provided by the vendor directly. And here, in the case of an ADC, the configuration is much more complex. So you can say which ADC you would like to use, then what pin it is, and you see that the pin is not following the Arduino standard. So here, these are really the pins that you can find on the pinout of the board. Then the sampling time, the clock prescaler, also the bit resolution. So here we are always using 12-bit precision, but you can decrease it if you want, and so on and so forth. Then the type of conversion. Then you see for the conversion mode, you can select if you want a software trigger or an external trigger. If you select an external, which one? So here it goes really a lot into details. And perhaps for someone who is not a specialist with C programming of hardware peripherals, perhaps it is better to start with the embed implementation. Then it's very simple, it will work. And if you want to optimize things later, then you can go to a specific STM32 implementation. And this, for search a system object, you can have access to the source code. I will not show you the source code of this one because it is very complicating, very complex, but I will show you the source code of an LED. So you see that was for the input. And if we go to the output here, so here you have also this embed or STM32 implementation. And if I go in the STM32, so now I can click on the source code, and this is how it looks like. So first, you do not need to learn a new programming language. System objects are done using MATLAB object-oriented programming. So that means that you will first create your class. In my case, it will be digital write STM32. And this class can inherit methods and attributes from other class, like, for example, MATLAB system and coder external dependency in this case. So in coder external dependency, you will have, for example, the sampling frequency. That will be an attribute that will be inherited directly there. And then perhaps I can just open the mask here again. Yes, you see, now you have the mask, and you can see that the properties that are non-tunable within this class, like GPIO port and GPIO pin, you can retrieve them there. So all what you write here will be reused and will be displayed in the mask. So for example, if I take a GPIO port, I click here, and then you can see that I have already populated the GPIO port that I am allowing to use. So for example, from A to F, I think, even to H, yes. So here you can just select that. And this way you can protect the user to enter some GPIO port that would be incorrect. And the same for the pin index. So it will go from 0 to 15. And you see these values are provided there. So this is a way to indeed verify that the input that is provided to an attribute of a class is correct. So these are for the input parameters. And then you need to define the methods of the system object. So here you will have a constructor in order to instantiate the class as an object. And then you will have the methods that you need to create for the system object. So the first one, this one is not that important. This is just to enable some options in the masks in case they are active or inactive. That's not the most important. What is important are the three next methods. So the first one is setup implementation, which is indeed the initialize function that will be generated with C code generation. Then you have the step implementation, which is the step function that will be called at every clock tick. And then you have the release implement method, which is indeed the terminate function. And now if we get a look at the code, for example, for this initialize function, so you can see that you can parameterize your system object so that it can work in in simulation mode. So here, if I'm not using code generation, I could provide a functionality to this block. Here I did nothing, but this is possible to do what we call the IO mode, which is something new since 2 or 3 releases, which indeed allows you to bring data from a real hardware peripheral in Simulink for the simulation in Simulink. And this is what is called the IO mode. But here I'm not using it. But it would be interesting in some cases if you want to get the real physical signals from a real hardware. And otherwise, when it comes to code generation, so this is this section there. So here first, I can include some specific header files from the hardware peripheral vendor. That's what I'm doing here. And then you see I can add some MATLAB code. So here I will just define a string or a char array. And then I will reuse the name defined here in order to create indeed some variables. So here I am creating variables by calling coder.opac. So I will create a uint32 variable of this name. Okay. The same for the following ones. And then here I'm creating a struct that is needed for my GPIO to be initialized correctly. And then once I have created the variables I need, I will call the coder directive coder.ceval to evaluate a C function. That's what I'm doing there. So here I will call the C function that is called enable clock, for example, and I will provide this input parameter. Okay, and I will do the same for the output mode to set the GPIO as input mode or output mode. And that's just for the initialization. So then once I have initialized my peripheral, then I can use it. And that is what is done in the step method. And here, basically what we will do, again, I declare the variables that I need. And then once I have done that, based on the input of my block. So here you see it's the input U. So if I go back there, so you see that's this input that is coming in. So based on the value of the input, if it is true, I will set the output pin to the high level. It can be value 1, for example. And if this is false, I will set the output pin to the low level. That's what I do. So you see, and I call the function set pin and reset pin that are provided from the vendor. And that's how you can do it. And then we have the terminate function at the end just to clean the GPIO port and so on. And that's it. But that's how you would do. And I would really recommend you to use system objects in order to create peripheral drivers. And here you mix MATLAB code and C code. And then when you generate code, you will see how it looks like. I will show you after. Okay. So let me go back to the presentation. We've discussed about this. Yes, then I talked about hardware support packages. So you have seen here in the library, the hardware support package for STM32. Then we have a lot of different hardware support packages for different hardware vendors you are using. And what the hardware support package will provide you on top of connectivity with hardware peripherals, it will also provide you what we call code replacement libraries. And code replacement libraries are indeed there in order to provide you optimized code for the specific processor architecture you are using. Perhaps you are familiar with the Neon library from ARM for the ARM Cortex-A processor. And here you can see that's a benchmark that has been done for finite impulse response filter, NFIR. So first, what has been done is that we have generated C code using simply the embedded coder without the code replacement library and without any optimization. And you can see that it took 410 microseconds to execute. So that's what we call 1. And then what we did is that we have activated some optimization settings in the embedded coder in order to optimize the generated code. And this time it went twice faster. Then we have enabled the Neon code replacement library that will indeed, instead of generating FIR C code that is not optimized for the target, it will reuse subroutines that are optimized for an FIR filter. And then in this case, you can see that the speedup is 24 times faster than the first implementation, which is really dramatic, I would say. There is a huge improvement there. And then finally, on top of the code replacement libraries, we have also optimized the settings of the embedded coder to reach a speedup of 29 times faster. So that's a big advantage of hardware support package, is that they provide also code replacement libraries that can help you speed up the execution of your algorithm onto your embedded system. Here we will use it as well. I will show you how it works. Okay, these are some examples of some of these subroutines that are available. And this is just a slide on hardware support packages to summarize what it can do. So it can provide support for peripherals. It can provide code replacement libraries. Also, it will install third-party tools, like, for example, if you need a specific compiler and so on. And it will allow you to communicate with the board to do external mode or processor in the loop verification. That's another slide on this, but I think that's quite clear. Okay, so now let's have a look to the processor in the loop verification using the external mode. So I will go back to Simulink. I think I can close some windows there. So that is this model for the external mode. Bring back MATLAB. I will close this. Okay. So now what I will do is that, so I have shown you before my hardware board. So now I have also some sensors that I will quickly stick on me so that we will do real-time measurements. So I just need to do that. In the meantime, I think I will already program the board. So here we are using this embed hardware abstraction layer. And what I told you before is that with the variants that I have set up, if I click on this button, so now I can implement the STM32 version of the algorithm everywhere. So now you see it is STM32. And if I go there, STM32 is selected. If I go here, STM32 is selected, and so on and so forth. But let's run it using this embed hardware abstraction layer. So I will just click again there to set it up. And now I will go to the hardware section and run it onto the hardware. So you see here the button is monitor and tune, because it will deploy the code onto the target. And then we will measure the signals. All the small Wi-Fi symbols that you can see there are signals that will be monitored by Simulink while the code is running onto the embedded target, which is very convenient if you would like to analyze the results and debug them afterwards. Also, you can change parameters on the fly. So here you see I have a dashboard button that allow me to reset the board, to reset the measurement onto the board. So instead of having a real physical button, I can have a virtual button there, and also virtual LEDs, so that we can see the status of the measurement onto the board. So now let me program the board, and in the meantime, I will quickly connect the sensors to myself. So I just have 3 sensors to connect. Just one more, and then I'm all set. Okay, ready. So here you can see the code generation process. Sorry, I just need to connect the board to the power supply. Otherwise, it will not work. I just need to generate the code again. So normally the code has been generated. Now it's fine. It will go faster, and then it will deploy it onto the board. Okay, so now you see code has been generated. Now it is compiling and linking the code. Okay. Now, yeah, when it opens this Windows Explorer window, that's to program the board. And now that's fine. So you can see that it is connected via the COM port 3 for the external mode. And now we can see how it looks like. So you see it is already measuring. So I will just stop it and start. Sorry, we just stop it, start it again. I will select already the reset button. I will just clean this measurement. I'm just doing that because then we can easily compare between processor in the loop implementation and standalone implementation. So I will restart it. Now it will start in the reset state. So then all the signals will be at 0. Just doing that to start in a clean state. Then it's easier to compare different implementations. Okay, so it is building the files. Now it is programming the board. I think I can close this window. Is set up. Okay, so now I am resetting. You can see that the reset LED is switched on. And then when it reaches 10 seconds, I will enable the start of the measurement. Okay, let's compute the value. After 5 seconds, it displays the reset. And now you can see the evolution of my beats per minute rate. So you can see that I am currently around 98, 97. So it's a bit high, I think. Not that high, but still a bit. Okay, so now it arrives soon at the end. So now the measurement is valid. Okay, so that means that now it will not modify the values anymore. So you see it remains at this value And at 50, I will switch it off, reset. So you see now I can reset it. And now I could restart the measurement, but I think you get the idea. So I will just stop it after 60 seconds. Okay. And now I have one measurement that has been stored here in the data inspector. And if I go there with the BPM mean value and I display the standard deviation as well, which is the computation of the error. So you can see that the signal was quite accurate during the measurement, because at the end we reached a value of 97 beats per minute with an error of ±5 beats. Okay, so that's fine in this case. And now the idea would be to do again this, but this time with the standalone deployment, because the goal is at the end to have it running in standalone mode. So here I have the standalone model. And the standalone model is exactly the same than the PIL model, except that this time we have this section here more and this area here more. So this area below is to display indeed the values onto the real 7-segment display. Okay. And here, what you have there is to send the data over the network via UDP or TCP for the intranet, or also via the IoT channel if you want to communicate to the cloud. So here I will not set up the communication to the cloud because I think there will be some lag because of the connectivity and so on. But it works. I just have a result I will show you at the end. But here what I will do is that I will do a local Ethernet communication by using UDP, for example. I will use also this embed hardware abstraction layer. So let's build and deploy the code onto the embedded system. And then, as you can imagine, so once the building process will be done out of my model, then the code will run in standalone mode onto the embedded hardware. And I will not need this Simulink model anymore. I can close it because there will be no connection with Simulink. Then, if I want to retrieve the data from the board, I will have to read the data coming in the UDP connection. And here you see also it has generated the report. And then we will come back after this to the report to have a look at the generated code. And this will be something very interesting for you, I think. Okay, so now the board has been programmed. Okay, I think now it's ready, so I can reset it on my side. Yes, you have to trust me, it works. So now I can close the model, and to show you that everything is fine, so I can open now a model that is called Get Ethernet Data. And this is a model I will run in Simulink just to read the data that are coming in from the UDP connection. So here you see I have this UDP block. I just need to provide the IP address of my embedded board to read the data, provide the type of data I'm going to read. And then once this is set up, I just need to unpack the bytes that I'm receiving, and then I can see the data there. So let's do a reset. Let's start the simulation. So you see now, when it will reach 10 seconds, I will release the reset button that is physically on the hardware system. Here we go. And now it starts with the measurement. And now we have again one signal. So let's see. So yeah, it's a bit the same than the one we did before in processor in the loop mode. I'm around 94, 95. So before I went to 96 or something like this. So let's see. And then you can see that here the LED is in blue to state that it is computing the result. Then it will become green. Okay, so now on the real hardware, the LED is also green. And then I will do a reset at 50, like I did before. Let's start with the reset. And then I will simply stop it right now at 60. So now I did two similar runs. Okay. And if I go to the data inspector, so now I can compare my two last runs, the one from the external mode hardware and the one out of which I collected the data from this Get Ethernet Data model. And here, so we can see that the results are not matching. It's because I have some time differences, I think, which is normal because I had to handle the process manually by pressing on the button. But let's have a look at the results. So if I look at BPM mean, so you see it's not that bad. That was not that badly synchronized. And so these are the two signals. So in the second measurement, we can see that my frequency rate was a bit lower. And I can also see the standard deviation, for example. So here you see at the end, the error on the measurement is the same. So we have just ±5, which is fine. And you see with this kind of interface, you can quickly compare the measurements that you did with the baseline that has already been set up for the specific test you would like to do. So now we have seen how we can deploy the code in different ways, how it runs in real time, and so on and so forth. So let's have a look at the generated code. So I will reopen the standalone model and open the generated report. So I think I will just redeploy it, and then the report will pop up. That will be pretty straightforward. And then here we will see, because I am using a code replacement library in this case for the ARM Cortex processor I'm using, and we will see how the code is replaced when it comes to use code replacement libraries. Also, if you want, I can then show you some optimization parameters that you have within the embedded coder for code generation. Okay, so now the report has been created. So you see it's another format than the one we have seen before, where you had the code side by side with the model. So now this is a report that you can share with a colleague who does not have MATLAB Simulink. The colleague will just need to use a web browser interface in order to open this HTML report. And now what is interesting is that you see you have several metrics. So here the static code metrics report does not work as such, because I am relying onto external C code for the hardware peripherals. That's why it cannot do an assessment on that. But otherwise, if you have C code that is only coming from the algorithmic part of your model, it will do an assessment of it. But for us, what is interesting is the code replacement report. So here you see I am using the code replacement library for the ARM Cortex-M, okay? And then it shows me there where this code replacement library has been used. So you see, for example, it has been used for this here in the, for example, sigma to u, or which one? There is the rectifier here, for example. So in the rectifier, the absolute value has been used using the fapps function from the code replacement library. Okay. And if now I double click on it, I can see here the code corresponding to the apps value, and you can see the fapps function that is there. And this function is not something that we have generated, but it's something that has been retaken from the code replacement library. Okay. And this is how you can take advantage of the architecture of the specific processor you would like to program. And then, as before, you can navigate back and forth between the model and the code. So here, for example, if I want to see where is this computed, I can just click on the subsystem, the block, and then it will show me where it is. And again, the code is readable. It can be customized a lot, even for your own standards within the company or something like this. So now perhaps what I can show you is when you go to the settings here, I will select the settings in the Simulink model. So you have the hardware implementation settings, and you also have the code generation settings. So when you go into the hardware implementation settings, so here you can select the board that you would like to program based on the hardware support packages that you have installed. So the list of boards here depend on your hardware support packages. So here you can see that I have several vendors that are available. So you just need to select one. And then once you have selected the corresponding one, it will automatically adapt all the parameters that are below. Like, for example, the size of the bits for specific data types. Also, what are indeed the connectivity capabilities. So here you see there is this connected I/O mode. That's the I/O mode I mentioned before, that you can bring data from the peripheral hardware into the simulation. And here you can just specify the serial port where it is installed, and that's it. Then for the Ethernet, you can specify the IP address of the board and so on and so forth. So this is for all connectivity, also for external mode. So here you see for external mode, I was saying that I was using the COM port 3 for serial communication protocol with the baud rate that you can specify, and so on and so forth. And then if you go to code generation, so here you have to select the target language compiler for the embedded coder. And once this is done, so you can select the toolchain. So here by default, the toolchain is automatically updated based on the hardware implementation selection that you did. But if you want to change that, you can. Okay. And then, so you see, you also have all the informations that are available for the template makefile, so on and so forth. And yes, you have quite some parameters when it comes to code optimization. So here, for example, so indeed, there are more than 1,000 different settings that you can tune in order to optimize and customize the generated code. And we have a training for that. So you can follow a 3 days training for the embedded coder only in order to handle all these settings. But perhaps one that is interesting is in interface. So interface here, this is where you can select the code replacement library. So you see, you can click on select, and these are the code replacement libraries that are available with the hardware support package that I have installed. And also, in case there are no code replacement library for the specific processor you have, but you have the subroutines from the vendor, you can create your own code replacement library and bring the subroutines from the vendor in MATLAB Simulink. That's also possible to create your own custom code replacement libraries. And yeah, so I think with that, I am 45 minutes. So yeah, we still have now 15 minutes for questions. So let me just go back to the slides to see if I have forgotten something. Standalone mode, we had a look at it. Yes, there is one polling question for you. So Jaren, if you can just start the polling question 4, that would be great, please. And let me go back here. Okay, so here the question is about the type of systems that you need to program at the end, if it is more embedded system or desktop computer, if you perhaps program also system on chips. So system on chips is multiprocessor architecture or also a mix of processors and FPGAs. Let's see the inputs that are coming in. So I can see, yeah, nobody, there are some others. Perhaps it would be interesting to see for the others, if you can just put in the chat, what are the other platforms you are programming? Just out of curiosity. Yeah, I see also system on chip is coming in. But most of you are programming desktop computers directly and embedded systems with processing. That's what is coming the most. 2 of you system on chip, 1 FPGA and 1 other. Yeah. That's interesting. Okay, so thank you very much. And then, yeah, this was just a comparison between several runs I did. I mean, it's not that important yet. And at the end, just to mention to you, so here with this demo, what is also possible is to send data over ThinkSpeak. So I don't know if you're aware of ThinkSpeak, but ThinkSpeak is a cloud solution from MathWorks. And what you can do is that from your edge node that is indeed in the field, you can send data over the internet via a data communication channel. And then the goal here in this example was to see if once that we have compressed the data, because you cannot send a lot of data over the network, you are limited physically by the amount of data you can send per second. But based on that, I could see if the data that have been compressed and so on, if I reprocess them after, if the ECG signal has still the same shape. And here you can see in red, this is the signal that was read out of ThinkSpeak when it has been compressed on the edge node side and decompressed on the other side. And in blue, that's the reference signal. And you can see that the shape of the signal has been preserved even through the compression process. So that was just to verify that the quality is not did not decrease. That's it. So I am at the end of this. So we still have 12 minutes for questions. So feel free to ask your questions.